In this video, I'll talk to you about the regularization. So what will you do when your model is overfitting? So overfitting basically is the model is fit too well to the training data but doesn't work well with the test data, which is actually unknown. So here there are several ways. One other way is to reduce the number of features. So we can do feature selection or transformation. For example, principal component analysis and select a few first dimensions. Another way is to use a regularization, and here we use all the features with reduced parameters theta, and each feature contributes a little bit to predict y. So how can we reduce the parameters theta? Right? Let's look at this. So this is the new cost function, regularized cost function, and you can see that we have a new term. This term is lambda times the sum of theta j squared, with j from 1 to n. So if lambda is chosen large enough, then the parameter theta j are reduced. So notice that this is a minimization problem, right? So this lambda is big, so when you minimize the cost function, it helps to shrink or minimize, shrink or reduce the parameter theta j. And note that we don't do regularization with theta naught. And if lambda is chosen too large, then all the parameters are penalized very much and are approximately equal to 0. So this may lead to an underfitting problem. We start from the original gradient descent update rule. Theta naught I is equal to 1 actually, right? And for j not equal to 0, you have hji at the end. And actually in general you just need this. This form covers everything. Now we look at the gradient descent algorithm, and here we need to have two update rules. One for theta naught and another is for other, because theta naught is normally not regularized. So this is the gradient descent algorithm. For theta naught, you don't have the regularization term at the end. For other theta other than theta naught, from the cost function, taking the derivative, you can see that there is another term at the end, and that terms actually come from here, right? Now we convert the update rule a little bit and combine that term with theta j, and what you have is this. This term is actually a little bit less than theta j, because 1 minus minus alpha times lambda divided by m is less than 1, because m is normally very large. And the second term here is the same as in the original algorithm. So the new theta here is smaller and smaller. And finally, this is the gradient descent algorithm, and this is for regularized linear regression. Normal equation can also use the regularization method. and the difference from the original theta is just this term, and I here is an identity matrix of psi n by n padded by a zero column and a 0 row, such that the psi becomes n plus 1 by n plus 1. So let's say if n is equal to 3, then I would be like this: an identity matrix and also padded by a 0 row and a 0 column. Now we look at the gradient descent for regularized logistic regression, and this is the regularized cost function. And you can see that it is actually from the original cost function added by this term, and you add this term in, right? And the derivative of this term, or the first term, is the same as that in the linear regression. So basically the algorithm is or look very the same, right? Except that the hypothesis for logistic regression is different, using a sigmoid logistic function.